All right, students, welcome into week, what's it, 12? I think it's week 12 for us. My goodness, let's see, I'll double check here. Let me see how many weeks. Yep. So we're in week 12, so we're coming up on just after Thursday's class. We're only going to have 3 more classes left to go. So we are coming up on the end. I say that and I hope it excites you because we're coming to the end of the class and, sort of the end of the journey. But also, I say that in case you're behind on the CK12 work, maybe perhaps behind on some discussion boards, perhaps. Keep in mind, we want to get those good and going. And so that way, we're not cramming everything into the last week because that's coming up in just a couple weeks here. Anyway, so we all know the deal by now. We know the routine. So I'm just going to hop right into it. And that way I can sort of not take up a whole half hour of your time. Hopefully we'll get a little bit less than that. All the stuff we know before, so we're going to hop down to our week 12 module, see all of our familiar friends. There's our link to CK12. This is the PowerPoint I'm about to go over. This is what you're watching right now. And then we have our discussion board. Whoops, that's for a different module. That's for next week. That was a sneak preview. That was like a secret scene at the end of one of those Marvel flicks, except it came at the beginning. That's why I don't make movies. Anyway, so all the familiar friends, just like before, the link to CK12, the Prezi presentation that I'm going to go over. What you're watching right now is the PowerPoint lecture, and then the discussion board on earthquakes. Now, the next 2 discussion boards are a little bit different than we've had in the past, and I'll show you real quick, because what I want you to do is I want you to draw on previous knowledge. Now we want to go back to plate tectonics, think what you learned about it, what you sort of learned in that unit and how it relates to earthquakes, and then for next week's volcanoes. And so what I do here is I just ask you, how are plate tectonics and earthquakes related? You can hop back to last week's stuff to see. You can Google some stuff to see, and you can sort of figure that out and reply to that question. And then the rest of these questions, so what happens at thrust fault boundaries, transform, and oceanic spreading ridges, you can find those directly on this website. So this links out. You can find those right on the first page. Do the discussion board, done and done. Keep in mind that is 10% of your grade. It is no joke. It can help you a lot, or it can be a pretty painful thorn in the side. So if we look at our CK12 work for the week, let's hop on over there. Oh, and you're going to get to see me release the unit, which is always a power trip for me. But anyway, back into our class here. If I go to our assignments, so we have, the ones that we've had in April, metamorphic rocks and plate tectonics introduction. And now we are going to assign earthquakes. The due date is the 29th. That is our last class, so have it done by then, please. And so I'm assigning it now, and you can sort of see as we hop into it, it's the familiar format. Now you do have 4 sections here. Earthquakes get a little involved, but I took it pretty easy on the quiz. The quiz is not super involved. It's not very long. I think it's less than 20 questions. But make sure that as you go through each of these sections, I know I've said this for the past 12 weeks, but I'm going to keep going at it. You have the articles to read, you have study aids, you have real-world examples, and those are all meant to get you ready for the adaptive practice, which is just a series of questions. You got to get 10 of them right. Once you do, you're done. But keep in mind, each section of the CK12 unit is required. We'll be talking tonight on how to sort of check your grade and how that sort of translates into it. But don't skip any of the parts on CK12. Now, if you've talked to me before about some sort of issue that has come up and we've made an arrangement to where, because some people they did a section and it didn't record it, or they did a quiz and it didn't record it, but I can see it on my end. Or if we've sort of talked things through before, those are the exceptions, but otherwise all sections are required. So 4 sections, then the earthquake quiz, and then you're done for the week. So let me hop over to, and then something you're going to see here, I do put some quiz questions into this week's lecture, so you got some freebie answers there. So I'm going to hop back to our presentation, and I'm going to get it going, so that way we can make this a nice, short little video here. So we go. All right, so the week 12 presentation, if I can say it. So it is by Anne Gamboa. She is the significant other of one of my college professors at Cal Poly. Very, very smart, and it's a great presentation, and it's really succinct. I like how compact it is, and I think you'll agree with me. So, and if you don't, well then, I don't know. That's fine. That's cool. You don't have to agree with me. But yeah, so let's talk about earthquakes. So I love earthquakes. It's one of the first, well, I don't love them. They intrigue me, but it's one of the first things that got me interested in geology. It was always a mind-blowing thing for me to think of the entire Earth shaking or significant parts of it shaking. And it's something we can't predict. It's just something that happens. Obviously there's factors into it, but the fact that it just comes like that is pretty amazing. Other parts of the country have like tornado season or hurricane season. There ain't no earthquake season. They just happen when they happen. They're kind of like if you ever have like a freak out, or if you get really mad at someone, you just like snap. That's an earthquake. Things can build up for a while, and then boom, things can go really bad really quickly. So let's talk about them. Definition of an earthquake is just the result of a sudden release of energy within the Earth's crust that creates what are called seismic waves. Just waves that move the material around. But so that's the best thing for us to define an earthquake as, just a sudden release of energy. So pressure and stress build up, and then that sudden release, whenever it happens, that's our earthquake. And so these occur because of a buildup of stress. Like I was saying, like if you ever had like a freak out or a breakdown, you were probably under a lot of stress. So forces per unit area that act on a material can create stress in the form of compression, tension, or shear. And these are the three we want to look at. So tensional stress, think of like pulling a rubber band. You can pull a rubber band only so far, and then it's going to snap and it's going to sting you, and it's just no good. But that is tensional stress when something's being pulled apart. And that's compared to compressional stress as things come together. And then the last one that we have is shear stress. Shear stress, it's not being pulled apart. It's not coming together. It's just simply sliding side by side. And so, this is our San Andreas fault, is a shear stress type of fault, where it's more of a side-to-side motion. But so, especially after the discussion board, you'll kind of know how each of these earthquakes happen. Compressional stress is what gives us thrust faults. Tensional stress creates, mid-ocean spreading centers and what's called normal faulting. And then shear stress, occurs at plate boundaries as well, and that's more of a transform motion. So when you see that in the discussion board, that's what it is. And then so strain. So strain is a little bit different. Things can be strained, meaning they sort of get deformed out of their original situation. It's just the deformation of materials in response to stress. So a stress will occur. That could be tension, it could be compression, it could be the strike slip or the shear motion, but it will deform the rocks, and they will partially sort of deform before they actually snap and break. So this is a photograph of a severely deformed sedimentary rock that's exposed in a road cut. When they make these roads, they'll cut into the rocks and they will expose some amazing geology. And so this is a road cut of the San Andreas Fault Zone. So you can see how much pressure and stress must be going on to create this wild formation here. So keep moving forward. And earthquakes always occur along faults. And so faults are just a fracture or a system of fractures in the Earth's crust that occurs when stress is applied. And it's applied too quickly, or the stress becomes too great, and it builds up. And so we're not talking about strain now. Now it's going to snap, and it's going to create that earthquake, that sudden release of energy. And so we could have horizontal faults. And so if you add compression into the horizontality of it, so if they're coming together, you get what's called a reverse fault. And we're going to see examples of this. But a reverse fault is also a thrust fault, but it's when one block gets pushed up above the other. And then we also have what are called a shear horizontal stress, which is strike slip fault. That's the side-by-side sliding motion. And then we also get what's called a normal fault, which is a tensional one where things are being pulled apart. So as things get pulled apart, you're going to have dropping down of part of the Earth's crust, and that creates a normal fault that we will see coming up here. So here we go. So that horizontal tension creates a normal fault to where one block slides down relative to the other. And that's sort of in contrast to a horizontal compression, which pushes a block above the other. So this is like a thrust fault. These are really dangerous ones. Normal faults are pretty common. It's normal to see them. I don't know. But especially in the basin and range, which is a big area of crustal thinning. So the crust is being pulled apart, and so you have a ton of these normal faults, as opposed to where two plates come together. Then you're going to have a lot of reverse faults because of that sort of compaction and that compressional motion. And then you can see the strike slip faults, which are the horizontal shear. So this is also called transform or transverse. You can see there's been no vertical motion. It's just simply side by side. just sort of offsetting things. And that offset, how this stream used to be, whoops, come back. It won't let me go back. Oh, it sent me back to the beginning, so bear with me for just a second. Okay, so to where these ones, had a vertical component, but the offset here from the horizontal movement sort of gives geologists an idea of how far it's moved over time and like how things used to look in the past. And so this river, which has now been offset, is evidence of a strike-slip fault. Alrighty, so earthquakes come with waves, and so the first one that we want to talk about is P waves. So P waves are seismic waves that squeeze and pull rocks in the same direction that the wave travels. Parallel. So these waves travel parallel in the same direction that the wave travels. And there's this push-pull, sort of accordion squeeze-pull motion that goes with it. So you can see this top graphic right here. These little lines are meant to sort of show compression when they get really close to each other. And when they're further apart, that's sort of the accordion nature of it, like the compression and the release, compression and the release. And that's opposed to S waves, which are seismic waves that cause rock particles to move at right angles to the direction of the wave. So if the wave is running this way, we'll say it's straight up and down, P waves are going to run parallel with it, but S waves will run perpendicular to it. And these are the ones that cause most of the shock, most of the damage, most of the shaking. The P waves, they can pass right by you and you never know. They don't do that much damage. The S waves, that's where the damage comes in. And so the P waves arrive first, and then the S waves come in second and just mess things up. And so here's a little video of how they would go. So we could see P waves here. Come on, play the video. It's making a fool out of me. Okay, here we go. So you see these P waves, just that compression, almost like accordion nature going through, all the way through there. To where the S waves, really, I got one little clip of that. Okay, so now when we look at the S waves, we see that up and down motion. So the wave is still traveling this way, but now the crustal motion is this up and down. So that's where it's perpendicular as to where the P wave was not perpendicular. It was parallel to it. Alrighty. So now with surface waves, or S waves, we have a couple different types. So we have one that's called a Rayleigh wave. So the Rayleigh wave is just this almost like elliptical motion, this up and down sort of when you hear people describe earthquakes, if they'll be like, oh, it felt like I was on a boat. I was just bouncing up and down. Well, that's probably a Rayleigh wave. We also have what's called a love wave. And it's not as romantic as it sounds because it creates a lot of destruction and sad times. Maybe it is just like love. Maybe. I'm joking. But no, the love waves move side to side. If you hear people say like, yeah, I felt like I was being tossed from side to side. Well, they experienced a love wave. It sounds really weird, but it's named after the scientists who discover them. So you can see the graphic down here. This Rayleigh wave is almost like if you were going over a bunch of, of hills and whatnot. Toward the love wave is just like if you were just shaking all about like a snake. That's the motion you would experience during that earthquake. And there's different components that go into whether or not there'll be like a love wave or a Rayleigh wave. It has to do with fault geometry, fault distance, material, ton of stuff we're not getting into. But one of the things we do want to look at is the focus of an earthquake. And so the focus is the point of the initial fault rupture within the earth. Now, we always hear them say like, oh, the epicenter of the earthquake was in Los Angeles, California. Epicenter is completely different from the focus. Focus is the point where the rocks rupture below the surface. You can see it on here on the graphic. And then if you follow that straight up to the surface, that's what your epicenter is. So the epicenter is the point on Earth's surface directly above the focus of an earthquake. So if they were to say like, oh, the epicenter was, at Montclair High School. Well, then if you stood at Montclair High School, you may have to go down a pretty deep ways, but you're going to hit the exact point where those rocks broke and the earthquake began. Pretty cool. All right. And so these are different ways of recording earthquakes. So we have seismometers and seismograms. And essentially, a seismogram is produced from a seismometer. And it's usually just about suspending a mass with some sort of writing utensil. And so that way, when motion starts, you can judge the vertical, you can judge the horizontal movement based off of that mass moving and the pen sort of writing on the paper. We kind of know this as the Richter scale. So the Richter scale is one of the most classic things that you see whenever there's an earthquake and you turn on the news. They'll show like the Richter scale and how it was just going before, and then ba 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 ba. The whole big earthquake going on, and that's exactly how an earthquake sounds, by the way. So just there you go. Sorry, but anyway, it's just a numerical scale. It's almost sort of outdated. It's nice because it gives a good visual, but we have much better ways of calculating the magnitude of an earthquake or just assessing the strength of an earthquake. I'm gonna take a quick drink of water here. This lecture is brought to you by LaCroix, so I'm having a LaCroix here. It's not really brought to you by it, but I need a drink of water, so hold on. And we're back. Okay, so when we talked about plate tectonics, earthquakes were a major sort of contributor to developing that theory because we talked about P and S waves, but when we sort of deal with the layers of the Earth, we know that this outer core is liquid. Well, if you take, liquid, think about it if you had a tub. If you had a tub full of liquid, probably water, let's hope it's water, but you got a tub full of water and you pushed it together like that compressional P wave motion, the water will compress. And so they noticed that the P waves made their way from wherever the earthquake happened all the way through to the other side of the planet. The P waves were arriving. The S waves, however, those stopped once they reached that liquid outer core. And the reason for that is if you take that same tub of water and you try to shear it, you can't really shear the water. The molecules in the water are already sort of free, and they're not technically free, but they're loosely held as compared to like a solid. And so you can't really shear water. And so those created what was called like a shadow zone, that there was no S or P waves occurring in these areas because they sort of got absorbed and sort of canceled out in this liquid inner core. And so that was a cool way for them to sort of understand, okay, we got like a liquid outer core that might be causing these convection cycles, which lead to plate tectonics. It all ties together. And so other ways that we have of determining the magnitude. So the measure of the energy released during an earthquake, which can be described using the Richter scale, is what's called the magnitude. So that's the measure of the energy that's released. So if you hear like, oh, was it 6.2? 6.2 was the magnitude. And the thing you want to remember about the magnitude part is it's not just like a linear scale. Like, oh, it's if you go from a 4 to a 5, it's 10 times greater. It's actually a logarithmic scale, which means that if you go from a 4 to a 5, it's 32 times greater than the previous one. So if you go from a 6 to a 7, it may sound like, 6 is terrible, 7 probably about the same, just a little worse. But no, it's extremely worse because it's 32 times more powerful. And so there's little, little side notes here you can sort of look at. 7 to 7.9 is a major earthquake. 6 range earthquakes, still very devastating, especially around like populated areas. And then, we have some of these earthquakes like 2s and 3s. We have them daily. We have them all the time. Sometimes they're just so small we can't feel them, but we're always having earthquakes. I think we're having one right now. I'm sorry, I was moving the computer like it at me. I'm sorry. But anyway, so we have also what's called the moment magnitude scale. So this is a scale that's used to measure earthquakes, believe it or not. I'm joking. So a scale used to measure earthquakes magnitude, taking into account the size of the fault and the rupture area of the fault. It also looks at the rock's stiffness, if you will, how hard the rock is, because as we've seen, different rocks are composed of different things, which have different strengths. And it also takes into account the amount of movement along the fault. And so we're not going to get into how you calculate all this, but the moment magnitude scale takes into account a lot of these other factors, which gives us a little bit of a better accuracy than something like the Richter scale. So that's just a way that we sort of measure earthquakes. And so it says here, let's see if I missed anything. The amount of movement along the fault using values that can be estimated from the size of several types of seismic waves. So they use the geometry, the length, and the length of the rupture to sort of factor in how strong and powerful was this earthquake really. And so the modified Mercalli scale. So this measures earthquake intensity on a scale from 1 to XII, which would be 12, so 1 to 12. And then the higher the number, the greater the damage the earthquake has caused. And so this scale is based more on how much damage does it do. Because if you look on like the USGS site, we have, not we personally, but like the planet has earthquakes that are like 6s, 7s, 8s, quite frequently. Like the 8s, maybe a couple a year, but sometimes they're so deep within the earth that they don't cause any damage on the surface. And so this scale sort of uses more of a how much damage did it do as compared to just simply how big was it on the Richter scale. And so in order to determine the location of earthquakes, if we were in class, we would do this exercise together. But essentially, they need 3 seismometers recording the earthquake, and they do some calculations based off of P and S wave arrival times. And then what they do is from wherever that location is, they swing a circle out using just like a regular old compass. And they do that 3 times with 3 different stations of information. And then where they all meet, well, then boom, there's your epicenter. Well, now that you know the epicenter, if you just drop straight down, you're going to find the focus of that earthquake. So this can also help them locate new earthquake faults. It's pretty cool. And so this is just a U.S. seismic risk map, pretty much meaning what's your risk of having an earthquake based off of where you live. And we live right over here in this bright pink area, so we have a very high seismic hazard because of being so close to the San Andreas Fault. And then also right up by the mountains, we have the Cucamonga Fault. And then we have, the Lake Elsinore Fault. We have the Puente Hills Fault. We have the Rose Canyon Fault. We are surrounded by faults. And that's why our seismic risk is so much greater than, somebody living up here in, the great state of Minnesota. They don't have to worry about earthquakes at all. But, you're also living in Minnesota, and it gets to be like negative 60 degrees. So I'll take a little bit of shaking if it means I get sunshine. I'll take that risk. And then so, we talked about, if we were in class, we'd spend some time talking about the San Francisco earthquake and sort of all the knowledge that came out of that. But this is just almost like another seismic risk hazard based off of the faults. So you can see the San Andreas Fault right up here coming from the top left corner and running right down through San Francisco. And it kind of gives you a probability of earthquake occurrences. This is the most we can do for predicting earthquakes, saying, okay, there's a bunch of faults here. They normally, produce an earthquake every X amount of years. It's been so many years since we've had one. Therefore, there's this high of a percentage of an earthquake occurring. That's as close as we can get. We cannot predict these things. It's just a matter of when do things snap. And if you care to, there's a video here with the San Francisco earthquake, seeing some of the damage that was done. I mean, my goodness, to tear apart the earth like this, you're talking about some serious forces. And, just devastated the city. Fires raged. It was a pretty devastating event. And if you want, there's a video on it. I'm not going to share it here because I'm trying to make this, lecture short and sweet. So with that being the case, I want to take you through a couple questions that you will see on the quiz. So I'm going to present this out, and this will give you some quiz freebies. So one of the questions you're going to see is the first seismic waves to arise at a seismic station are, and we know because we just saw, the P waves. They're the primary waves, the first waves, the pressure waves. And so that would be your answer on that one would be D, the P waves. And then which of the following is the place of origin of an earthquake? Well, now we have a couple options here. So we know it's not seismic zone or none of the above. We talked about the focus and the epicenter and how they are both different. Now, this says the place of origin. So even though the epicenter is the area on the surface where they can say the earthquake took place, the actual origin of the earthquake would be directly down in what would be the focus. So the focus on this one is your answer. That's a little bit of a harder one. That's why I wanted to go over it. Now, the theory that stress builds up along a fault until it breaks, causing an earthquake is, it's not continental drift. It's not plate tectonics. It's not even something we talked about in our lecture, just because I don't want to go over too much stuff that we don't focus on too much. But it's actually called the elastic rebound theory. Think of elastic like, in like your underwear or, I guess rubber band too. I shouldn't just jump straight to underwear. But the elasticity is coming, like being able to stretch it out and then coming back to normal shape. But as we not even elastically, as we put stress and strain on these rocks, they will sort of snap and then lock back into place, almost like an elastic rebound. So on that one, C would be your best answer. So stress builds up on rocks. They go under a blanket, cry, eat some Haagen-Dazs, watch some romantic comedies, try to cheer themselves up. No, nothing like that. When stress builds up on rock, they will deform plastically and then break. That sounds like everything we were just talking about. So as the stress builds up, you're going to have that strain, which kind of like moves the rock around, and all of a sudden it can't take it anymore. Then, bang, it ruptures and we have an earthquake. So we'll take A. That's a really good answer. With B, rocks don't always just break. Sometimes they strain, they deform. They don't need to break all the time. And then immediately have an earthquake? No, because you need to let the stress build up, and then you'll have the earthquake. And then none of these is incorrect. So you'd want to go with A on that one. And this is just a nice little true or false, and it's very relevant to the area we're living in. And so along the San Andreas Fault, the Pacific Plate is moving southwest relative to the North American Plate. Okay, well, you're going to be looking at that in the CK12 unit, but essentially what we have is, let's say I have to look at like a reverse sort of thing here since I'm looking at my little picture down the box here, or my little video. But anyway, so we have we'll call this the North American Plate, and this is the Pacific Plate. But the motion has shown us that the Pacific Plate is actually going up to the northwest in reference or in relativity to the North American Plate. So this one would actually be false. It is not moving southwest, it is moving northwest. And there are so many faults in the San Francisco Bay Area because the movement must be taken up by all the faults together. So this one, when we saw on the Prezi presentation, like that map of San Francisco and all of those faults. So anytime there's a fault, they can transfer stress to another one because it's almost like, if I was holding a bunch of books in each hand and then someone put, or let's say I had like a little plate here or a wooden board. Say I had a 2x4 and I was holding it. And people started to put more weight on each side while I would have to accommodate by, that stress transferring to one hand to another. And so these faults sort of work in the same way. They can take up the stress and strain put on other faults. And in the San Francisco Bay Area, since we have the San Andreas Fault system, which is a series of faults, this would absolutely be true. So this one kind of goes back to our plate tectonics. That's why I wanted to touch on it. So a subducting plate plunging into the what is a difficult process. It's a difficult process, I like how they put it there, and causes quakes. So yes, one of the things we know, a subducting plate going back down into the earth. What is it going back down into? Essentially is what this question is saying. It's poorly worded, so that's why I wanted to talk about it. But the subducting plate will go down into the mantle. So it's not just the crust, like the crust is what's being subducted. So the plate is the crust. The lithospheric plate is considered the crust. And so it is diving down into the mantle, and as it moves down into there, it will cause earthquakes. There you go. There's some freebie answers for you and a nice quick little video. I look forward to seeing you all in the Zoom, and we are coming close to the end, so stay up on CK12, stay up on your discussion boards, and I'll talk to you soon.